Goedemiddag welkom op deze laatste sessie van machinering. Het is altijd een uitdaging voor de sprekers om die laatste sessie te begeisteren. Maar ik zou zeggen, voor iedereen die luistert, stay sharp. Waarover gaat het bij de presentatie van Rob en Roel? Hoe en wanneer controleer je slijtage van snijgereedschappen? Groot vraagteken bij mij. Roel en Rob ontwikkelden een datagedreven monitoringmodel om dit probleem preventief al een beetje te kunnen inschatten. Ik geef het podium aan Roel en Rob. Geef hen een warm welkomstapplaus. Dank u wel.
Hello. So first of all, is there anybody who prefers English over Dutch? Yes? Okay. Then we'll do it in English for you. All right. So I'm Rob Salaets from Flanders Make. I'm a research engineer at Flanders Make. But you might wonder, what is Flanders Make? I'm trying to advance the slide. All right. So Flanders Make is the Flemish Research Institute for Manufacturing. That means that we do research projects and try to bridge the gap between research done at universities to bring it into the industry. So that means that we start from quite low technology readiness level technologies and try to increase the market readiness level and try to make it more robust and more cost effective to actually use these technologies in industry. So we are in between industry and the universities. Our key topics are typically making production elements smarter, making machines smarter, and making vehicles smarter. So think about autonomous vehicles, autonomous AGVs in a factory, drones doing inventory counting in a warehouse, things like that. And we define new roadmaps for the Flemish industry. Okay, thank you. New roadmaps for the research tracks that would benefit the companies the most. And we try to transfer the knowledge coming initially from universities, making it better, and getting those new and hype technologies at the companies. So what I will be talking about today is a technology we developed to track the sharpness of cutting tools, and we have validated a new measuring principle that allows you to reconstruct cutting tools such as milling tools and drills in 3D, and this allows you to do precise monitoring of the sharpness of your cutting tools. And we made this with low-cost components and also quite decoupled from the CNC machine itself. So this means that it's an ideal solution to retrofit on existing, maybe older machines, because there is very little connection required with the CNC machine. So why would you want to track the sharpness? Of course, to avoid quality issues, because machining with blunt tools and worn tools will affect quality a lot. And of course, it's also a quite fast check inside the CNC machine. So this means you can do it relatively often, and you don't have to unmount the cutting tools. So some tools wear out quite unpredictably. For example, if you're drilling into composite materials, due to the structure of the material, you can have quite fast wear, or for some materials, the tool wear occurs rapidly. So to track the sharpness closely, you need to do these measurements quite often. For example, in between production runs, or even during a longer production run. And so what we do is we reconstruct the geometry at the beginning of the tool life, so without doing any operations. This gives you this 3D profile you can see. And then after the tool degrades, you do these measurements again and again, and then you see how the cutting edge was worn here a lot, and you see how the cutting edge is too sharp, too dull to continue. And then by overlaying the two geometries, we can actually quantify the distance between the surfaces, and this gives you also insight in how the tool is wearing, and this allows you to search for also for the why question. Can I maybe change my cutting parameters to reduce this type of wear? And yeah, this is of course very valuable information. So here I have again the motivation on one slide. If you want high quality parts, you need sharp cutting tools, and for sharp cutting tools, you need to regularly check your tools. Now, I know there are things like pre-setters for machines which do this offline, and so there you have a microscope looking at the tool, which still needs a human or a sort of an AI solution to analyze magnified pictures of your tool. There's also things like laser-based technologies, for example, from Blum or similar companies. Even sometimes manual inspection where they just use the naked eye is used, and then we know that this detection can go up to 100 micron, which is not enough to detect slight tool wear issues. So manual inspection or this offline inspection takes a lot of time, so it would be nice to do that inside the CNC machine, so you can go for low manned production and automate the process. This results in maximizing the tool life, of course, and then you don't need to change to very conservative maintenance schedules because you know exactly it's there in 3D where and how much tool wear you have. I have some trouble advancing the slide. Okay. So I've said it already, more autonomous operations of CNC machines. You can avoid downtimes due to cutting tool issues. You can detect when the tool is broken as well with the system. You can replace costly cutting tools exactly at the right time. And in the beginning, I also said our solution allows for retrofitting on older machines because there's no connection needed except for reading out the coordinate values. And getting this 3D reconstruction is very valuable information because you know where your tool wear is occurring, and also this gives insight in how you can solve it. So laser-based systems, they also give you this information, but not exactly where the tool is wearing down. And for a laser-based system, you always need to know as well the geometry of the tool in order to move right to the near to the laser beam, while our system can do this without having precise knowledge of where your tool is. So I have also here the results on this slide. We can do a measurement cycle in 30 seconds. We have an accuracy of 60 micron, which is maybe quite a lot, but we use low-cost components. But the most important figure here is the 10 micron repeatability, because this is what allows us to do accurate comparisons between our original geometry and the measured geometry of a worn tool. So, okay, how does this now work? We have a line scan camera, which is a one-dimensional camera, a horizontal line of pixels, which is looking at a spinning tool while it is backlit with a collimated light source. A collimated light source means that the light is as much parallel as possible. And then we are looking at the shadow of a spinning drill. And we're then taking slow motion videos, let's say, of the spinning drill, which exhibit as a digital caliper. So this, by looking at the width of the shadow, we get enough information to reconstruct one cross-section of the tool, and then by stacking up the cross-sections, we get the 3D reconstruction. We also need an encoder in the spindle or a tachometer to synchronize our camera measurements. So this means 3 simple components where the encoder is usually already available, and then you just have to place the camera and the light source somewhere in the CNC space, and we can do a measurement by making the tool spin in front of the camera and drop in tiny steps of, let's say, 50 micron while spinning. So these are the type of videos the camera can make. So in the horizontal axis we have the time, and you see how the shadow width is fluctuating while measurements are done. And then we do this for a few steps along the drill, and this allows us to reconstruct the geometry. So this is an overview of the full flow. By taking one vertical line of this image, we have this shadow profile. We need to associate the width of it. And we do that for every point, and then we get a 2D reconstruction of a cross-section, and then we stack up those slices. So if you look at the rotating tool, you see how it produces these 2 shadow edges. And then we can see that in both the left and the right edge there is the same information, but it's just shifted by 180 degrees. So this signal we use to reconstruct the convex part of the geometry. And this allows you to reconstruct the convex part, so that means you cannot look into the cavities. But that's also a limitation of, for example, laser-based systems. But is that a big problem? No, not so much, because the cutting edges are always the convex parts, and the tool wears down at the parts where it touches the material it's cutting through. So we believe we can still detect the wear occurring at the corners. And then this is a step where we overlay the original geometry with our new measured geometry, and then we can just quantify the difference between the surfaces. And then we can highlight in this way where the tool wear has occurred and how much wear is there. So we did an experiment by drilling with a cheap drill you can buy in the Gamma, for example, and then drilling a few holes in stainless steel, which is of course a very hard material. And after even a few holes, your tool is it's almost useless. As you can see, the cutting edge is entirely gone. And this is just an example to illustrate visually. We can analyze this is a worn tool, but even for much smaller values of where our system can be used. Now, I hear you thinking, well, up until now, I've only seen drilling tools, but can you also do it for milling tools? Here I have an example of a 3-flute milling tool and a multi-phase milling tool, where you can again see this limitation of not being able to reconstruct in the cavities. But as I said before, that's not a big issue because the tool wear occurs only at the edges. Some other examples of useful things you can do with this. It's the same with the tool presetters. You can use this camera to estimate the tool length and also give an estimate of the tool runout. Another thing is you can use this exact geometry to compensate for your actual tool width. So you can compensate your CNC machine to, if the diameter is slightly smaller than the original geometry, then you can compensate for that. So as you see, this is a lab result. We've tested it on in a lab environment, but of course the CNC environment is something else. So we validated the measurement principle, and now we're looking for a partner to bring it from a proof of concept to a polished and robust solution, such as the laser-based cutting tool monitoring solutions that already exist. Because you have a very harsh environment with lubricants flying around and chips flying around. So there needs to be a sort of a protection layer around it for this measurement principle to work. But this is an example of a new measurement principle that we discovered that have some advantages over the existing technology. And then we bring it to the industry and we look for an integrator who can integrate this in their machine tool and then get it by the Flemish companies. And then this kind of data is something you can also use to learn more about your production process and optimize it. And this is exactly what Roel will talk about.
Yes, indeed. Good afternoon, everyone. My name is Roel van Thillo. I'm a business developer at Flanders Make. And I will talk today about gaining actionable insights from production data, heterogeneous production data, so meaning across the end-to-end production process using a knowledge graph. So what Rob presented to you was how we improve a single production step using measurement data. But what if you want to look broader than that? What if you want to look at the entire production process using data from different departments, from different silos, to answer more complex questions than just how can we improve our quality by monitoring the sharpness of drills? Okay. So behind me you can see an example of a production process where historically, as you know, knowledge data, they are structured in kind of data silos, which is fine if you are looking at those specific process steps, but which becomes quite complex if you want to answer questions like, how does the sharpness of my drill influence the final quality of my end product? In that case, you will have to gather data from the cutting tool, but you will also have to gather data from the end test of the product. You have to combine them and you have to do an analysis. How does one influence the other? And does one influence the other? That's also a question. So a couple of examples here for more complex questions where we use data from different data silos. As you can see, the questions themselves are not super complex, but you will need data from the different areas to answer them. And where it does get complex is that those data, they're different. You have time series data. You have, different kind of databases. You have implicit information, so knowledge from the engineers, from the people who are in the sourcing department. You have technical structure differences, so people without the knowledge might not be able to understand a certain document. So they have to go to engineers, to other people to figure out what is it about. And then, because the data is so spread, the knowledge is so spread, it's virtually impossible or very hard to do ad hoc analysis. So you cannot answer these questions just in 5 minutes. You basically, if you want to do it properly, you need a data scientist that can drill down into the different data silos, that can figure out where is the data, what do I need to get, how do I need to structure it to make it usable. And you need that data scientist to talk to the people that have the knowledge. So someone that is doing that is losing so much time just gathering the data, not even getting the insights, that we thought at Flanders Make that there has to be a way to make that better. So we did an analysis, and I don't think we're there yet. I'm going a bit too quick. So we did an analysis on different available technologies. But first, I want to do a quick comparison with a tool that you all will know, business intelligence, which is currently a popular method to evaluate data across a certain process. But it has limitations. You can only answer rather simple questions. You have to clean up and curate your data up front, and it's not flexible. You cannot ask it new questions without developing the whole setup first. So to do the ad hoc analysis, you need a lot of time from a data scientist. So we did an analysis of the available technologies, and we found that a knowledge graph would be or could be one of the most viable options to improve this process. And what is a knowledge graph? It's basically a knowledge database that is using a graph structure or graph structure to integrate data. So it's an overarching layer across all of your data structures that maps the domain model for your entire end-to-end manufacturing process, and also builds the relationship between the entities in that process. I won't go in too much detail here, but it basically consists out of two main blocks, which is the domain model that describes the different blocks, entities in your process. So think back about the example that I showed earlier. Your CNC machines could be one type of entity. Your materials could be another, and you can think very broadly. But the goal of that is to map the entire process and to map also the relationships in between. And then the second layer below that is the data, where you link each of the entities to the specific data point it relates to. This could be a database, this could be knowledge from a person, this could be information that is available in the company. And here I made a small video and I hope it works. Yeah, let's see. So the typical way to question a knowledge graph or to look at a knowledge graph is using tools for which you need technical knowledge. It's not usable by a person that didn't study to be a data scientist, let's say. So we have built a graphical user interface to enable also a non-technical user, any kind of manager, to explore the full domain model that you have. And here you see a simple model of a drilling operation where we have a hole, a plate, and a drill. And in the example, you see that I try to find some correlations between the attributes of the entities, where on the right side you have a graph that is plotting the data that for which you select the entities, as well as the databases from which the data is pulled, and an overview of the query that is built or that is used to retrieve the data from those databases. Okay. But the knowledge graph in itself is only the start. It's only about getting the actionable insights. But as Rob was showing, once you get the insights, you have to do something with it. With those insights, you have a piece of information, but if you don't take action, it doesn't matter. So using those insights, the next step is building models, which you can then input in what we call a streaming or a live digital twin. So you can actually monitor for the steps that you want to monitor, for the questions that you have. You can monitor your process in real time, combining the data that you get in real time from the process with the models to answer the questions that you have. And as an example, here we created a very simple dashboard to monitor the quality of a hole, let's say, where you combine both the production data as monitoring data as the quality of the drill or the sharpness of the drill to see if the hole that is being drilled is according to the standards that you set. And here you can then basically build information, messages, alerts to the operator in case thresholds are being crossed and action needs to happen. So that concludes our presentation. If you have any questions, feel free to contact us, or we'll be right beside here afterwards.
We have also a demonstrator right besides the bar where you can see the optical setup in action.
Roel en Rob, bedankt voor jullie uitleg. Van beide trouwens. Ook van jouw laatste stuk. Maar jij bent meer bezig met business development. Gericht naar mijn vraag naar jullie beiden toe, want jij bent eigenlijk, ze zeggen, de brains. Je bent de developer naar de klant toe, naar de wens van de klant toe. Hoe kunnen mensen met jullie samenwerken?
Er zijn verschillende opties. De ene kant is het het onderzoek dat gesubsidieerd wordt door de Vlaamse overheid. Dus dat zijn meer lange termijn projecten die gaan rond topics die belangrijk zijn voor de meer algemene Vlaamse industrie. En daar werken we meestal samen met een consortium van 3 tot 6 bedrijven rond één bepaald thema. Waar dat dan ook kleinere projectjes specifiek voor de bedrijven worden gedaan tijdens...
Kunnen mensen die met jullie samenwerken daar ook een subsidiering voor krijgen? Of hoe zit dat dan?
Ja, mensen die met ons samenwerken kunnen daar ook subsidiering voor krijgen via Vlaio.
Ja.
Maar dat moet dan kaderen in een onderzoek of
in een juiste onderzoek. Oké,
Vlaio.
heren, dank u wel. Zoals voorgesteld, er staat een demonstrator aan de bar. Ik kan gerust een koffie of iets anders nuttiger gratis met de heren en de demo bijwonen. Ik dank u van harte. Ik heb nog iets voor jullie. Ik zal het u sowieso meegeven, maar ik zou zeggen, geef de mannen een warm applaus. Dank u wel.